Thanks very much for inviting me. What I'm going to do is I'm going to show you some of the projects that we've done in the Antarctic, but they're a bit meaningless if I don't give you a little bit of background. So you have to kind of imagine yourself going back to school, and we're going to do some very basic kind of geography lesson just at the very beginning, just to help you kind of position the place that we're talking about. So if I start first of all, and we'll just do the map, the world's map. And it's all very simple because Antarctica is the little bit at the bottom. It's the white bit at the bottom. It's where penguins live, just in case there's any doubt. And the bit at the top, that's where the polar bears live. So we're doing mostly penguin land for, I'd say, 90% or 95% of the talk, and then we'll just touch on the polar bear territory just at the very end. So this is a map of Antarctica. Antarctica itself is around 58 times the size of the UK. It's roughly the size of America and Mexico joined together. And it's the 6th largest continent on the planet. But in the middle of winter, the sea freezes for 600 miles out from the coast of Antarctica, at which point it grows to the 4th largest continent on the planet. And it holds 90% of the world's fresh water frozen in its body. And at the centre, the South Pole, the ice is about 5 or 6 kilometres thick, so it is really covered in ice. I think there's 2% where it melts during the summer period, but otherwise totally covered in ice. But it's also a very dynamic continent, because changes in sea temperature that have taken place over the last 100 years and which are accelerating significantly at the moment are creating dramatic change in the Antarctic. And I'll talk a little bit about that later on. The South Pole has an American station, and the station I'm going to talk about first of all is called Halley. It's a British research station, and it's at 75 degrees south, which means it's about 900 miles from the South Pole. And Britain has 2 big stations in Antarctica, has one at Halley, and then, I don't know if there's a pointer, I'll just point anyway. It's the other station is up here at a place called Rothera. And when you join Rothera to the South Pole and the South Pole to Halley, that is the area of Antarctica that traditionally Britain has claimed, although all the countries have renounced their claim to the Antarctic recently in a process of collaboration under a special treaty. But nonetheless, our stations are positioned there just in case we have the opportunity to restate that claim. That's okay. And we've positioned our stations absolutely at the edges of our territorial claim. Now, some countries, they maintain their claim by having some soldiers there or an airport. But the British, we maintain our claim by having 2 stations, and we mark their territory by having a post office at each of them.
You can click there.
Yeah, brilliant, yeah. Oh, can I flick for the slides as well? Oh, right, okay, that's good. So next little exercise of geography. This is showing the kind of physical position of Halley Research Station. So the brown bit is the continent of Antarctica, which rises from the sea up to a height of about 2,000 or 3,000 meters at the center. And then it's covered in 5,000 meters of ice above that. And the ice flows from that high-level plateau off the continent, off towards the sea. So here you see the snow and the ice flowing off, and as it hits the sea, it carries on and it floats on the sea as giant ice shelves. And Halley is floating on one of these ice shelves. So actually it's not even on the main continent of Antarctica, it is bobbing about on the ocean somewhere off the coast. And because it's on the coast, it's in a very dynamic location because the ice is always flowing, so it's constantly flowing away from the landmass. And also, because it's at a low level, winds which start at the top of the plateau come down the slope of the ice shelf and they buffet that station at speeds in excess of 100 miles an hour. So it's moving, It's floating, it's hit by winds in excess of 100 miles an hour, and surprisingly, it's quite cold. And this is what bits of the station look like. This is Halley 5. This is the predecessor to our design. This is actually one of 3 buildings that they have at the station. Oops, sorry. So, as I say, it's located on an ice shelf. The ice shelf itself is about 150 metres thick, and it's flowing at a speed of around 400 metres per year out to sea. And now I was just going to tell you about some of the main issues of climate that they have to deal with at the station. Before I do that, I'll just show you, this is a picture of the Halley 5 base. So, which is, the pointer is the bit in the middle, is it? That bit? Yeah, there we go, excellent. So this is the ice shelf, all this flat white. That's all you can see when you go to Halley. There's no scenery, there's no mountains, there's no wildlife. You can see occasional reflections of the distant sea on the clouds on the horizon, which is a slightly bizarre mirage type effect. But otherwise, there are no features. The only features being the buildings that make up the station. And there are 4, and we can see 3 of them here. This one here is the main living platform. That's what everybody sleeps in. There's a garage, and then there's these 2 buildings. These 2 buildings are science platforms. One is for meteorology, and this one here is for studying outer space. And that's where, for 20 years, a group of 16 people were living in the winter and around 50 or 60 in the summer. And as I said, it is cold. In the height of the summer, the maximum temperature is about -3, so not dissimilar to outside here today. In the depths of winter, the lowest recorded temperature is -56, and as a general rule, between May, June, July and August, the temperature fluctuates between about -40 and about -50. That means in the depths of winter, all the vehicles which they keep on the base to help maintain it become totally inoperable. This is what happens, for example, to the bulldozers. They just get totally caked in ice and snow and they can't be used. So at the coldest point in the year is when you suddenly start having to do everything by hand. And then as the temperature rises in the summer, so the air speeds start increasing because the pressure drops, and all of a sudden you have ferocious winds of around about 100 miles an hour, and these winds pick up little ice and snow crystals off the surface of the ice shelf all around, and they literally sandblast everything round and about. So just technically, in terms of the surfaces of things, you've got to make sure that they can stand up to this constant, aggressive battering by ice crystals. Now, because it's on the coast, you get higher levels of precipitation. So you get high snowfall, and then you get high winds causing drifting. So every year, the level of the snow rises by about 1.5 meters. This is quite a sort of complicated geographical feature to get in one's mind, because the snow never melts, it snows, so the snow level rises, but the sort of physical altitude of the station doesn't change, because as the snow increases, so the ice shelf gets pushed down and the sea eats away some of the ice at the bottom. So the thickness always stays at around about 150 meters, even though the level, even though if you leave something on the surface, it will get totally buried. And that's exactly what's happening with Halley 5, the current or just previous station, is that year on year, the snow level is rising by 1.5 meters. Anything you leave on the surface gets buried, and so therefore they have to deal with that by looking at ways in which they can elevate the building above the snow to stop it being buried. And that in itself is a very complicated process. So I don't know if you remember the building that was off in the top corner of the slide, which I said was the main habitat building. That has 20 steel legs. And those steel legs elevate that building about 4 meters above the snow level. But because the snow level is rising by 1.5 meters every year, they need to jack it every year using electric screw jacks attached to the legs, which help to just push it up another 1.5 meters. But because the legs are only a certain length, they have to weld some steel on the top of those legs, And then they have an additional problem. The ice moves like water. It literally flows one plane over another. So those 20 legs all get distorted in different directions. So one's going that way, another's going that way, one's going that way, and the legs all start pushing themselves in different directions. So every summer, a steel crew used to have to go out to Halley 5, and they used to grind off the legs at the snow surface. Then they'd straighten up the leg above, and they'd weld in one of these big steel plates here, and then weld the leg back to the steel plate. And then when they'd finished that, everybody on base works together to then jack the station up. And so what's happening is, oops, I'll just go back to that one there. What's happening here is they've welded that plate in there. So this part of the leg, that's last year's bit of leg, that's going down there. But the next bit of leg is just going to go up here, and then the next year it'll probably go there, and then the next bit there, and then the next bit there, and then it's literally all over the place. And the bottom is now about 30 metres below the ice surface. Anyway, once they've done that alignment, which takes around about 6 or 7 weeks, 6 or 7 people doing that job, then everybody on the base is needed to then man one of these special scaffold baskets and one of the electric screw jacks to gently lift the building up the 1.5 metres that's needed. And it takes them about 3 days doing that. And that's really great when the sun is hitting the building and you're sort of basking in the sunshine. But in the summer, the sun rotates all the way around the building because it never sets, because you're in the bottom of the southern hemisphere. And as a consequence, when the sun moves off your basket, suddenly you're working at minus 20 degrees, holding bolts and spanners, and it becomes a very, very cold process. Now, this is the inside of Halley 5, the previous base. So you're all architects. So probably you could do a slightly better job than that. This building was only designed by engineers. And we can see that it's reasonably comfortable, but it's also incredibly institutional. And you have to add to that the fact that people are living. There's only 15 or 16 of them on a winter's crew. The winter lasts from February all the way through to December. So the winter period is 10 months long. There's 16 of you just living on the base. There's no access by aeroplane or ship, so you're totally isolated. And then you add to that the cold, the wind, and then the next issue to do with human isolation is 3 months of total darkness. So these people in the middle of, from about the middle of May through June, July to the middle of August will not see the sun rise. And all they will see are these spectacularly starry skies and displays of the southern lights. But they have some neighbours. And these are their neighbours, a colony of emperor penguins, which they go and visit every now and then. When it comes to December, the base is restocked. So that's the one time of the year that they get any fresh food. So for about 2 weeks in December, they eat fresh salads, fresh vegetables, and fruit. Otherwise, everything is tinned or everything is frozen. And what happens is a supply ship operated by the British Antarctic Survey sails from South Africa or from the Falkland Islands, carrying the summer crew who carry out maintenance and introduce new experiments. And these people all arrive with all the supplies at the edge of the sea ice, which by this stage has melted. So it's no longer 600 miles out from the coast. It's only 1 or 2 miles out from the coast. And the ship moors up against the sea ice, unloads everything onto the sea ice, and then tractors drag all those supplies across the sea ice to the ice shelf, where they use bulldozers to make a ramp in the edge of the ice shelf and then drag it onto the ice shelf and off to the new base. Now that has with it some high levels of risk, because the sea ice is not 150 metres thick, it's 2 metres thick in the thickest bit, which means it can only carry loads of about 9 tonnes, which isn't that much. It's probably like the load of a bus. So when you're carrying things across, you have to be very careful that you don't hit a soft patch. And one of the adaptations that the British Antarctic Survey made after this incident was to introduce hatches into the tops of all their vehicles, so that when it does do this, the guy can jump out of the top rather than having to open the door, which may be a bit too late. Now you might think, well, why don't you carry everything in by plane? But the site is very, very remote, and there's no proper runway. So the only planes that can land are these little twin otters, which have got skis instead of wheels, and they can take off over a very short distance. But the problem is they need to be refueled very often. So at the start of every operational season, they have to use the twin otters to deliver little supplies of petrol all over the Antarctic so that they can make the journey from one base to another. So this is on a journey which I made, actually, and we flew from one of the British bases off across to Halley, and we had to land on this thing called the Ronnie Ice Shelf and refuel with some barrels of fuel which had been left there. You have to leave the engines running. The first thing is when you land to do the refuel, the pilot comes in and he uses his skis and he just touches the ice surface, but he doesn't land. He just takes off and does a circuit. And as he's on his circuit, he looks back to where his skis touched the ice to make sure that no crevasses have opened up, because obviously he doesn't want to land in a crevasse, and nor did I. And then he comes back, and if everything's all right, then he touches down. He leaves the engines running, and the crew, who was us, get out and help refuel the aeroplane, all the time leaving the engine running. And then when everything's done, off you go, take off, carry on the journey. But at that point, I think we were the only people for most definitely 1,000 miles in every direction, which is a very strange feeling. So you might think, well, it sounds a horrendous place. Why would anybody want to work or live in a place like Halley? And the answer is very simple. It's because the science is worth it. So I'll just briefly explain why. First thing, 1985, 3 British scientists working at Halley discovered the hole in the ozone layer, which is probably one of the most important environmental discoveries of the last 30 years, and it led to the signing of the Montreal Protocol, which banned the use of CFCs, which again is one of the most important pieces of environmental legislation probably introduced around the world. So in addition to studying ozone and climate, Halley is also a fantastic, what we call a window on space. It's at 75 degrees south, which is one of the best zones on the planet for investigating the interaction between the sun and the earth. And incredible research is carried out there into the thickness of the outer atmosphere and the impact of solar particles bombarding the Earth's atmosphere. And those kinds of pieces of research are what give us the information about global warming. So it is absolutely at the forefront of the research which is telling us about changes in the Earth and the systems which govern the operation of the Earth. But Halley has a very, very big problem. Halley 5 has a very big problem. Because as I mentioned, the ice is flowing off from the main continent. So this is the main continent down here. The ice is flowing in this direction here. All this stuff here is bobbing about on the ocean. But it's grounded on an outcrop of rocks here and the edge of the continent just here. And so where it's grounded, it starts flowing slightly slower. So a crack is appearing here, and there's another crack here. And the crack will slowly follow this dashed line. And as you can see, Halley 5 is on the wrong side of the dashed line, with its legs stuck 30 metres down in the ice. And that causes, obviously, a significant problem. There's about 5 or 10 years predicted until all the stuff off to the left, which is about the size of Wales, disappears on a giant iceberg. So as a consequence, the British Antarctic Survey realised they needed to do something. And, of course, when you need to do anything, the best thing to do is to hold an architectural competition. So that's exactly what they did. They held an architectural competition to come up with a wholly new way of designing a research station which would help them to overcome this problem that they'd had. Halley 5 is named because there had been before it. The problem of all the previous stations all disappearing on an iceberg. So they had this competition to find a design for a relocatable station. They had 86 entries from around the world. 6 teams were shortlisted to develop their designs. Then they chose 3 who then did a much more detailed design. And then out of that, we were very lucky to win the competition. And before I show you our design, I just thought I'd just give you a whistle-stop tour through this is the next section after geography, the history of Antarctic architecture. And you might be thinking, God, blimey, this bloke's going to go on forever. But the truth of it is, it's a very, very short subject. It's 100 years long, but there's probably only 3 different building types. This is the first type. The buildings here and here, these are the 2 huts built by Captain Scott on his 2 different expeditions to the Antarctic. This guy here, he's the first guy ever to have flown over the South Pole. He's in his hut. And that there is the first Halley station, built in 1957. And it was built, again, as a timber hut. You can see this is probably in about 1960. So there's been about 4.5 to 5 metres of snow, and it started to bury the station. But they kept on living with it. But they found that, of course, they couldn't use the doors any longer, so they had to make shafts that then came out of the roof and climbed down into the building. And then eventually, the dynamic flow of the ice crushed it. So they thought, well, probably these kind of huts aren't the best solution. Bearing in mind everything gets buried, let's design buildings to get buried. So the next generation of stations, Halleys 2, 3 and 4, were all built as these tunnels and with habitation inside that you allow the snow to accumulate on top. And here you can see there's a shaft where you, as the snow rises, that's got staircases in it, and then you can go down the staircase into your underground tunnel that you then live in. And that was, well, I suppose, reasonably successful. Those stations lasted for about between sort of 7 or 8 to 10 years each. But by the end of their life, it was pretty grim because the ice is moving all around you. It starts cracking and distorting the outside envelope of the building, which you can hear at night. You hear the ice creaking all around you when you're in an underground building like that. And then, of course, you've got to remember you've got things like kitchens, bathrooms, and, of course, the sewage treatment plant are all in the tunnel with you. So not only is it creaking, not only have you got no view, but you've also surrounded by the smell of sewage all day long. So quite quickly, just before I go on to the next stage, this is the vast view, actually, of Halley 3. So it is a tunnel. This is, you can see it, this is where it's just poking out of the edge of the ice sheet before being dropped into the sea. So, having lived underground for a number of years, the scientists and technical staff who man research stations in the Antarctic thought, do you know what, this is really not that successful and it's actually quite depressing. But nonetheless, they needed to deal with this issue of rising snow levels. So the solution was to build buildings which are elevated. And Halley 5, the building I showed you, is probably one of the first elevated stations. And then this is the very most recent generation of elevated buildings built above the snow level and which incorporate hydraulic legs, allowing the foundations to be lifted up and new snow to be pushed underneath to allow the stations to rise above that constantly rising snow level. So there's a French-Italian base in a place called Concordia. This is the South Pole station, the American station. This is a German station, a place called Neumayer. And this is a Belgian station, which is only used in the summer. And certainly the American, the French-Italian, and the German have all use a hydraulic system to enable them to literally lift themselves above the rising snow level, whereas the Belgian station is built on a rocky outcrop, so the wind itself clears the snow from underneath. But of course, at Halley, we faced an altogether different problem. We faced the problem of the building also disappearing on the icebergs at the point that the ice shelf starts to crack away from the main continent. So we needed to build the first ever fully relocatable research station. And here you can see one of the earlier CGIs. It looks very similar, in fact, to the finished product, which is probably good. And our concept was really very simple. It was to go for a modular solution. So the modules are then of a size that they can be pulled using big tractors and bulldozers to a new location when there's the risk that the site might disappear on an iceberg. The stations are lifted up on legs, which also have hydraulics, so that they can be elevated above the rising snow level. And the legs are supported on skis, which provide really good foundations for dissipating the load across the ice, but also can be used for that relocation process. So our basic building block is what we call our standard or blue module, and those blue modules are used for the majority of the activities on the station. So on the right-hand side is a bedroom module. So they're used to house bedrooms, offices, doctor's surgery, air traffic control room, servers, places to hang your coats, laboratories, offices, research spaces. So pretty much everything that's needed for daily life. They're also used to house all the plant, generators, sewage treatment facilities, fuel, fire suppression systems, water treatment systems, and so on. So they really are the basic building block of the new station. And when it comes to the relocation, each one of those modules can utilise the hydraulics to lower down closer to the ice surface, bringing its centre of gravity down to closer to the ice. They can be rigged up with steel bars and then use the skis and tractors to be pulled to a new location. Within each of the modules, the start planning device was really the bedrooms. And a lot of thought had to go into the bedrooms because we wanted them to be comfortable, but we didn't want them to be so comfortable that people just hide in their bedrooms at the expense of the overall community. So they have a place that you can sit and work at a desk. They've got quite a bit of storage, a nice view onto the ice, but they're not so comfortable that you can have loads of people in your room or that you can hide in there watching TV or literally escaping from the community. In the winter, you get a room to yourself. In the summer, you share with somebody who's coming in, sometimes for a few days, sometimes for 2 or 3 months. And this is the kind of basic plan of a module. So you had 4 bedrooms, either side of a central corridor, and to break down the feeling of corridor, we have enlarged threshold spaces where you move from one module to another, where there are then, gives you access into things like the toilets, the showers, storage rooms, but also views out into the landscape. So there were spaces of light and dark as you move along that corridor. The corridor widens out where you get the doors into each of the bedrooms, and it also has a higher ceiling with roof lights in to allow some light in the summer. Within the bedrooms, one of the areas which we put in a lot of research was looking at how to help people overcome the issues of 3 months of darkness. Because in the darkness, you can have this terrible problem of falling into a sort of biological free fall, where, because it's always dark, you stop recognising the time to get up. So instead of getting up at 8 o'clock or 9 o'clock in the morning, you get up an hour later, and then the next day, another hour later. And before you know it, you're getting up at 8 o'clock at night or 9 o'clock at night, and all your friends are still getting up in the morning. And that can cause real stress and anxiety. So we worked with Philips and our lighting engineer to come up with this light that you see here, which incorporates an alarm clock and daylight simulation lamps in it, so that you can program that for the time that you want to wake up in the morning. And the light rises like a rising sun next to your head, just to help re-establish your balance of red and white blood cells, to just give a small device, sort of like a little espresso shot, to kickstart your day. We also worked in our team with a colour psychologist called Angela Wright, and she developed a special palette of colours that we've tried to use through the majority of the station. She called it the Spring Palette, and the idea was both to assist wayfinding, but again to give a sort of bright palette which helped people overcome that constant issue of darkness and seasonal affective disorder that you get in the winter. And through that use of then colour, volume, thresholds, we were really working as a very sort of elementary architectural level to try and make sure that each module became a sort of place in its own right, that you felt every time you entered a module that this was a point to sort of stop, to breathe, to think, all right, I'm doing this, I know where I am in the station, rather than just having one single width, long corridor running along the whole building. And you might be thinking, oh, I wonder why you even had to have them in a straight line, and I'll come to that in a minute, but it was a very important climatic feature which forced us to do that. As well as being a place to live, Halley is also a place of phenomenal scientific research. And one of the most important features of that is to give as much flexibility to allow significant changes in direction of scientific research to take place. So each of the modules has a three-dimensional space frame substructure, which gives lots of space for service distribution within a warm envelope. And then its superstructure is all on the outside. So all the walls and ceilings can be demounted and changed when we need to account for different experiments, different requirements of the scientific experiments that are taking place. So, with that whole concept, we were able to accommodate virtually all the features that are required of an Antarctic research station. But there was one thing we were having real trouble with, and that was the main communal space. Because it just couldn't fit in one of these blue modules, you needed more space than that for kitchens, dining rooms, a bar, other recreational spaces. So the solution was to then design what we call the central module, which is the focal point of the whole design. And this is a two-story module. One of those blue modules is about 160 square meters in floor area. This one's about 360 square meters, so it's a bit more than double the size, on 2 floors, with as much open plan space at the lower level as possible, so that you get people having a meal, playing pool, in the bar, all sort of doing everything together. And that was a very important design decision, because we had noticed in a lot of stations that they had broken down activities into cellular spaces, and you started getting very disruptive cliques building. So you'd get the gym clique, and they wouldn't allow, the odd tubby bloke like myself to come in and just do half an hour a week. And then you'd get worse than that, you'd get the drinking clique. And so they would shut the door on the bar, and then, someone who just fancied the odd beer felt uncomfortable opening the door, hearing them all having such a good time inside. So we were very keen to break down as many of these potential cliquey barriers, just with very simple, open plan designs for space. Within this central module, however, we realised we needed to have some quieter zones for watching TV, for people to do internet access. And so there on the upstairs, we introduced a special helical stair for getting up to the upstairs as a sort of focal point of that module. And then there are 2 other features in here, neither of which, unfortunately, we've been able to include. One is a greenhouse which grows fruit and vegetables using nutrient-enriched water. It's a process called hydroponics. There's all the infrastructure in there. The idea was that would give people salads during the long winters, but we haven't managed to install that as yet. The other feature, we thought, well, people in the Antarctic are really outdoorsy. They all love doing skiing and kite surfing and, loads of sort of cool outdoor stuff. So I thought we'd better bring a little bit of that inside. So as an alternative to the stair, we introduced a climbing wall as the means to get from the lower level to the upper level. And to start with, they thought, yeah, that's a really great idea, until the health and safety officer pointed out that the climbing wall is just next to the bar, and the two may be sort of mutually exclusive. So they decided to get rid of one of them. These are just some views from a fly-through we had done, which show the inside. So you can see the open plan spaces on the top 2 shots, and then some of the more enclosed spaces on the upper level. And on the 2 main spaces in the upper level, we have these big domed roof lights. And the point of those was that you could then walk into those and be fully enclosed in glass, so that in the winter, when you get the southern lights flashing all around you, you could have that experience as a sort of full semi-dome experience happening all around you, which is a pretty awesome experience in its own right. Now, this is the explanation as to why the station is arranged in a straight line. For 95% of the time, the wind blows from one direction only, east-northeast. So the wind blows towards the modules, and then as it passes underneath, it then starts decelerating again and drops it in giant drifts. And this was from a computer fluid dynamic model, which was done by a special firm of wind and snow engineers just from Guelph outside Toronto. who were predicting where the big drifts would take place on our building. When we went to see them to start with, we had an arrangement that was sort of more like an X shape with our central module at the middle. And they very quickly demonstrated to us that the first line of the X the wind would accelerate underneath, pick up snow, and then it would very quickly bury the second line of the X. So they said, this is what you have to do to get this building to work. And we thought, well, that's all great. We've had computer models done, but we need to be really sure that this drifting analysis is all going to work. So we did some smoke testing in the Building Research Establishment in Watford. And then we also had these scale models built. And we put them on the ice at Halley. And then the scientists did this process where they worked out that if you got a wind of a certain speed on a certain day at 1 to 50, that would equate to the wind through a whole winter season. So we put these modules down facing the direction of the prevailing wind, and then one night there was this big storm, which they say equated to a whole winter season of storms at 1 to 50. And then we got snow drifting all around, but we could see that the wind speeding up underneath had cleared all the snow and ice away from the ski-based foundations, keeping them free from snow. So having established that it was going to be a line, we then had to decide which things went where. So we put all the sleeping off to the north end with the main sort of what we call the command module, which is where the base commander and the doctor and air traffic control and so on are in here. Then our main social module, and then at this end, 2 science modules, and then here, 2 of those mechanical equipment modules, so that you could have generators in both. And then we separated them with a bridge. And the reason we did that is because if there's some catastrophic failure or a fire in here, then you could escape and live in here until you can be rescued. And you might not be rescued for 6 months. There's no fire service, there's no support structure, nobody to come and get you, and it's too cold to fly an aeroplane in and too difficult to get a ship there. So you've got to be able to look after yourself until the emergency services can get in. So that bridge is really there as a giant fire barrier between one half of the station and the other. Now, I thought I'd just quickly explain to you how that whole jacking process works with the building to show you how it rises up out of the snow. So here you have a module in cross-section at the end of a year of snowfall. So the wind is blowing in this direction here. So it's 1.5 meters above the building. The wind hits here, speeds up under here, picks all the snow that otherwise would have accumulated here, and then starts forming a giant drift heading off towards Madame Tussauds. And then what we then do is we use the bulldozer, lift the legs up, push new snow underneath, and then jack the building in small little measures to raise it above the snow level to get it all on a level again. And I'll show you a movie of the sort of final effect of that a little later on. The next technical issue was how do we make the outsides of one of these buildings? And we looked at all sorts of different solutions, highly insulated timber panels, highly insulated metal panels. But in the end, we settled to use glass fibre panels. Glass fibre is used quite often in the Antarctic because you can make very large panels, which makes the construction much simpler. But also, glass fibre is thermally relatively unconductive, about 100 times less conductive, for example, than metal. And so you get much less expansion and contraction between the cold and when the sun hits your building. So your joints between panels are more stable, so you risk losing less heat through your envelope. And here are just some of the earlier examples of glass fibre panels. These panels at the French-Italian base are that height from there down to there, which is about 20 metres high. This is a South African base on an island off the Antarctic, a small little pod used by the Germans, and then another South African base. And all of those had used glass fibre relatively satisfactorily, so we opted to go down the same line. I won't go into the nitty-gritty of the detail, except to mention 2 things. One is that our glass fibre panels, they're about 200 millimetres thick, and they're fixed back to a steel structure. And the glass fibre was made in a vacuum, and we had glass fibre strands connecting the inside to the outside, so that when you get really massive suction from the wind, you don't get the outer skin being ripped away from the inner skin. And we used a special kind of insulation called polyisocyrenate, which has closed cells of foam, so that you don't get any water migrating through the foam from one side to the other and freezing in the process. The development of those panels took an enormous amount of time, because they have thermally very demanding criteria that they need to meet, but they also had very high levels of fire resistance that they had to meet. And combining those two processes in glass fibre panels was not easy, but it was achieved in the end. In terms of energy, we wanted to use sustainable measures like wind and solar. The trouble with the wind is that the wind blows so fast in such fierce gusts that most attempts to introduce turbines have ended up with the turbines scattered in small pieces all around the station. And this is a German turbine. It's supposed to operate at 20 kilowatts, which is quite a lot of power, but they have to keep the brakes on and run it at 1 kilowatt, otherwise the turbine has a habit of flying off the shaft. We have got the capacity to introduce solar power, to use it for heating up water in the summer when it's bright sunshine all the time. But of course you only get the sunshine in the summer, and you don't get any solar energy in the winter. So in the end we've used generators, but they're special kind of generators, combined heat and power generators, which means that you can catch the heat off the generator as it makes electricity and then use that heat to heat up the building. So actually we don't have to generate any special heat to heat the building. It all comes as a consequence of the electrical demand for things like science experiments, TVs, computers and the like. We also had to max out on prefabrication. So here you can see the sort of base structure and services of a module, which is this three-dimensional space frame, and all those services pre-installed as long cassettes that can then be slotted into the structure. So in terms of the plan, off to the left-hand side, that's one of the main energy modules. That's got most of the sort of big gumph that you need to make the building operate: generators, water treatment systems, fuel, and so on. But then each module in its own right has a smaller little plant room, which has got all the air handling and humidification and the hydraulics which drive those legs. And the reason that we have those smaller plant rooms is then you can just duct the air round one module in itself without having to have ducts passing from one module to the other, which, because the modules might move slightly differently to each other, might end up with cracks and things like that happening in those ducts. In terms of water production, in the summer, it's a really good fun communal activity. Everybody gets their spade out, and they dig snow and they shovel it down a great big shaft which has got a big heating element in the bottom, and it melts water, which can then be used for showers, for cooking and so on. And that's really good fun in the summer. You chat, having a laugh. Winter time, it's slightly harder. So here they are having to wear helmets so that they don't get their faces ripped apart by the ice crystals that are being blown around at 100 miles an hour. We've overcome that to a degree by having bigger surface level shipping containers with heating elements in, and then you can just lift a lid and shovel snow in for most of the year using a bulldozer. But in the winter they still have to get this, in the depths of winter, for about 4 or 5 weeks they still have to get the shovels out. In terms of water usage, we introduced lots of special fittings which reduce the amount of water that was necessary. It's a kind of bizarre thing with water production in the Antarctic. You're surrounded, as I mentioned at the beginning, by 90% of the world's fresh water, but it's all frozen. And to create the water you need to drink, you have to melt it, which uses a lot of energy, which needs a lot of fuel, which is really expensive to deliver. So water production becomes a very carefully managed process. If you have a shower, you're not allowed to have a shower for more than 2 minutes. You're supposed to turn the shower on, get wet, turn it off, put all the soap on, turn the shower back on again, get the soap off, quickly get out again. So it's not a kind of, there's no long lounging around in the bath when you're in the Antarctic. When you brush your teeth, put the toothpaste on the toothbrush, get it wet, turn the tap off. Everything is very conscious of using as little water as possible. But still, in the UK, we probably, as a rule, each of us use about 160 litres of water a day through our own hygiene and through cooking and drinking and so on. At Halley 5, they'd cut that down to 100 litres a day. At Halley 6, we've cut it down to 50 litres a day. And the main significant change we've made, apart from the sort of more updated fittings, is we've got a vacuum drainage system like you get on an aeroplane, which then means that instead of using 9 litres of water to flush a toilet, you're only using between half and 1 litre. So it's had a significant impact on reducing the water usage and therefore the energy that's needed to melt the ice and therefore the fuel which they need on the base. So as a consequence of all that, we've actually cut down the amount of fuel to operate the base by 26% per square metre compared to the previous station. Now, in terms of construction, we started building around 5 years ago, but you can only build in a very short 10-week period when you can get the construction crew through. So we had to maximise the amount of prefabrication and testing that was done before we started. First thing we did is we built some test sledges to make sure that we were going to be able to pull those modules, each of which was going to weigh about 80 or 90 tonnes. That was all very successful. And here we are doing some of that fire testing that I mentioned. All our panels were made in Cape Town in South Africa. So here we are testing some of those. And then crucial to the process, we built some test modules to make sure that everything would fit together, that the hydraulics would work, that the cladding was as thermally efficient as we hoped it was going to be, and that the building was as airtight as we had presumed. And here you can see the test module for the big red building. And it just demonstrates the value of this process, because when we put this together, you can see there's a panel just here. It doesn't quite fit. And if you're 15,000 miles from the UK, or even 5,000 miles from South Africa, and 30 days sailing, that little problem can just be slightly a pain, because it means you can't get another panel for another year. But the benefit of building this test module is that we were able to take that off overnight, take it back to the factory, trim it down to size, another one of the benefits of using glass fibre panels, and then slot it back in the next day, and it all fitted perfectly. Just after I took this picture, there was an enormous bang, and I thought, oh my God, something's collapsed. And so I went for a quick walk around, and then just behind, I saw 2 pickup trucks that had smashed headlong into each other while staring at this strange red thing in the middle of a residential community in Cape Town. So from Cape Town, everything was loaded onto this giant Russian icebreaker, the maximum sizes within the weight restrictions of that 2-metre thick sea ice. So this is the biggest component. It's the substructure frame of one of those modules. So unloaded onto the sea ice and then attached to a bulldozer that then pulls it across the sea ice up onto the ice shelf. And then when it arrives at the ice shelf, that's the top left-hand picture here, it's then hoisted up using a crane onto these 2 shipping containers. Then the heavier hydraulic legs with the bigger skis were then installed. And then when they're installed, they put on these prefabricated floor cassettes which provide a working platform from which to erect the rest of the module. Here you can see them installing some of the prefabricated services. So you can see those are drainage runs going in. And then here's some of the prefabricated components for some of the plant modules. We didn't really have much influence over the design, obviously, of some of this equipment, except they made one small mistake that the plant fabricator rang me up one day and he said, you can have any RAL colour you like for the fuel tanks. So I gave him a bright pink fuel tank, which hasn't gone down that well with some of the more macho mechanics who work on the station. Here you can see after that's installed, then the superstructure steel frame is then installed. In some of the other modules, the rooms were all prefabricated. So that means that bedrooms had all their furniture installed. So walls, floors, ceilings, bunk beds, desks, chairs, wardrobes, duvet was in there, pillow was in there, absolutely, completely finished. And then here with each of the modules with their prefabricated rooms, the superstructure installed. And then from there, the cladding goes on. And here you can see again, one of the benefits of using the glass fibre cladding is you can make really big panels which means that they can be installed quite quickly. So that panel that's being installed there is about 4.5 metres high and about 10.5 metres long. So it's a pretty sizable piece of construction. And it's being fixed back to the superstructure so that they were able to clad all the modules in one 8-week construction season, which is really pretty speedy. They were pre-installed with the glazing as well. And here you can see the red module having some of its prefabricated glazing installed. The whole construction was managed like a kind of factory line. So you had a team working on blue module cladding, a team working on blue module steel frames, a team working on the red module, so that everything was moving along at similar stages, almost like it was a product, which of course is one of the benefits of modularity. And then when all the cladding was on, we're now at the sort of middle of season 3, when all the cladding was on and some of the interiors had been installed, the modules were lowered down on their hydraulics and linked up to these bulldozers. And the reason they did that is that all the early construction had taken place at the site of Halley 5. And the reason for doing that was that then they could use the sleeping accommodation and the services of the chef and all the other infrastructure which existed at the old base to support the construction crew. But having got the modules to a certain stage, they then lowered them down, linked them up, and then pulled them to the site of the new station. And here you can see the red module disappearing off towards the Halley 6 site. It's about 15 kilometres away. And now I've got a short movie just showing that relocation of the red module.
Monday morning arrived, big red was hooked up and almost ready to go.
I think it's going to make this location. I think the difficult part will be actually bringing it into line with the tripod.
It's going to be about 160 tons. We're definitely over 200 tons with it. So, just out of our comfort zone slightly. But, good team on the job. Anybody can shift it, we can.
Surprisingly, it pulls out relatively easily for a 200-ton building.
And then once it arrived at the Halley 6 site, the modules were then all linked together. It took about an hour and a half to move one of those big modules from the Halley 5 site, 15 kilometres, to the Halley 6 site. And then it took the rest of the day to move them the last 50 millimetres to align them all together, which is a very complicated process. And here you can see after all the modules had been linked together. In terms of the linking, we use these giant bellows like you get that linking train carriages together. We got these from Scandinavia, where they were used them on trains which have to perform down to about -40, so they're pretty heavily insulated. And here you can see some of the service distribution within the space frames of the modules. And here the hydraulic leg, and there's a line of lighting underneath as well, which is just to help people when they're doing maintenance in the winter. And these flashing red beacons which light up when the hydraulics are in operation as a warning light.
Next, the modules.
This is the raising of the modules.
For jacking. The jacking frame is brought in. Snow is in film under the ski. The ski is then placed back onto a heap of snow. This continues all the way along the length of the station. Once all the legs are up, the first jacking takes place. Then the process is repeated for the second jacking. And the melt tank is placed back in.
And here we see everything all linked up and now fully operational. So inside now, people are living, working 900 miles from the South Pole inside the new station. These are some of the workshops, for example, for scientists. This man here, John Shanklin, one of the three people who discovered the hole in the ozone layer. This is his last visit to Antarctica before retiring, and he's using a machine there called a Dobson spectrophotometer to take measurements of the thickness of the ozone layer. So carrying on the groundbreaking research which he started, or which he discovered in 1985. On the tops of the science modules, we have these decks where there are all sorts of pieces of science equipment can be installed, taking measurements of the atmosphere, climate, and so on. And this is the main social module, the central module, and that white glass area, that's the double height space where people go up to the upper levels. The white glass is actually a very high performance insulated glazing which comes from Germany, insulated with a material called nanogel, which was developed initially for the space industry, which allows light to pass through but gives you a very high U-value performance. And then the black stuff is actually clear glass, but it's like sunglasses because you get so much reflection off the snow. And this is the inside of the central module. And the staircase leading up to some of the upper levels. And there you can see the impact of that white glass. So it lets a lot of light in, and then you get the clear views. I mean, you'd hardly believe that that black glass was giving you the clarity of view that you're seeing through there, but it's just like sunglasses, basically. And here's the upper level with those domed roof lights, which you can then stand in to look at the auroras in the middle of the winter. And then moving down the station towards the sleeping modules, you get things like the air traffic control room. It's a fantastic project, this, because you get little tiny bits of everything. So you get catering areas, science areas, a doctor's surgery with a full operating table. You get base commanders, and then here we've got an air traffic control centre. And then moving on further down, these are the bedrooms, the bedroom corridor, and then at the very end there's a space which we call the quiet lounge, where people can just escape from the community if they want to have a quiet time but they don't want to sit in their bedroom. And here, this is the very end of the station with that quiet lounge, which has its small balcony as well, which is used again for escape.
They have left their mark with this iconic structure in Antarctica, which will help facilitate science now and in the future. The last of the BAS staff head homeward on the JCR, leaving the 14 winters behind to start the day-to-day life of an Antarctic winter at Halley. 57th team to winter on the Bronte Shelf, and the first of many to winter in the new Halley 6 station.
I just thought I'd show you a couple of pictures from their first winter season. This one was taken on the day of the Queen's Diamond Jubilee. So they had tea and cake, and then naturally they went and played croquet and cricket underneath the module. So I knew we'd put those lights underneath for something useful. And then this is a picture of the station taken just a few weeks ago. And you can see, you might ask yourself, why would you ever want to spend a winter in a place like that? But as an opportunity to experience our planet with such clarity, it's pretty awesome, I think. And don't worry, just a very few slides left now, just to show how, having never designed anything like an Antarctic research station before, we've suddenly found that the experience of designing one has led to a few other opportunities in a similar area. So the first one of these came about a year or so after we started designing Halley for the Spanish. It's a slightly different location. Again, it was a competition. But whereas before we were competing on a level playing field with lots of other people who'd never designed research stations, suddenly we had a tiny advantage in that we'd done one ourselves. So managed to win this one. This is on an island off the Antarctic Peninsula, and it has very different conditions to Halley because here the snow does melt. It's one of the few places that the snow does melt. The wind doesn't come from any direction. It blows just constantly all around you, but it's not nearly as cold. It also is surrounded by extraordinary wildlife, whether that's leopard seals, or chinstrap penguins, or gentoo penguins, or these elephant seals, and in fact one of the very few flowering plants that you get in the Antarctic. So we had to be much more careful in our construction of the fragile ecology that existed all around. So rather than designing a building, in this case, in a line, we built modules, but much longer modules, because they didn't have to move, around a central circulation point. So when everyone's moving around the station, they keep having a point that they cross over so that they keep bumping into each other, which helps to kind of reaffirm the sense of community. And then somewhere off to the distance is a special module for doing all the science. But just like the people at Halley, the Spanish scientists working at Juan Carlos Base love the Antarctic environment. So we made sure that we had great big windows at the end of each of those runs to give them views onto the totally awesome scenery, mountain scenery that you get on Livingston Island. And here you can see that base. It's a year or two behind Halley, but now under construction. Then there was another competition, this time for a Korean base. So introducing a whole new layer of interest. We started off by investigating the way that snow deposits. If you leave buildings close to the surface, they should be run in line with the wind. If you elevate them up, they need to be perpendicular to the wind so that you can predict where the drifting occurs. But the Koreans were also very interested in a building which was overlaid with elements of traditional Korean culture, which in the Antarctic poses a significant architectural problem. But we cast our eyes, that's not the station. We cast our eyes round some of the more iconic buildings that one finds through history in Korea and noticed the significance of Gateway in terms of sort of demonstrating a transition from one life to another, from one level of being to another. And we use that notion of snow drifting and the technical requirements that it sets up with the idea of Gateway to then create this building, which places the primary accommodation in wings and then their main social module perpendicular to that, to create their own gateway to polar science. Then, from the Antarctic, we have now moved up into the Arctic. And at the start of this year, we won another competition, in fact, this time for the American National Science Foundation, who operate a station at a place called Summit, which unsurprisingly is the highest point in Greenland. And it sits at the top of the Greenland ice cap, and it's around 800 or 900 miles from the coast. And the commission here is not to design the whole station, hopefully that'll follow on. To start with, it's to design a laboratory. And this laboratory they call an atmospheric research laboratory, and it basically benchmarks levels of pollution in the air around the world. So they're looking for the purest measurement they can in the northern hemisphere, which they get at the top of the Greenland ice cap. But in order to get the purest measurement, they can't have any pollution in or around this laboratory. That's not just pollution from vehicles, that's pollution from materials. So they can't have any materials which give off any gas which will disrupt any single one of their measurements. And they're not talking about a tiny amount of gas, they're talking about mega minuscule measures of gas. So every single construction component has to pass through the laboratory of an organisation called NOAA, which is the National Oceanographic and Atmospheric Administration, who have to test every material to make sure that it won't disrupt any of the experiments. Nonetheless, the solution is quite similar. It's an elevated module, this time utilising much more solar energy to help meet the electrical demand. It stands on its own. It's actually bigger than one of the blue modules at Halley. And inside, it's just empty. It's full of space to house incredibly technical equipment, which is making these atmospheric measurements, but also measurements on the outer layers of the atmosphere. And with that, I thought I'd just leave you with a shot of a winter aurora at Halley. And I'm done, so thank you very much.
Take some questions.
Yeah, if anyone's got any questions, please, fire away.
Can we have this as a screensaver?
Yeah, you can, yeah, that's fine.